We will now look at finding the volume of an object using the disk method. And this is used to define particular types of objects. The idea is that we have some function that we want to bound at x equal to a and b, and we consider the region between this function and the x-axis. We're then going to take that area and rotate it around the x-axis. And when we do, we get this actual volume. We get this three-dimensional object. And this is called a solid of revolution, because that's what we did. We took something and we revolved it around the x-axis, and that gave us a solid. The disk method lets us find the volume of these solids of revolution. In particular, what it says is that the volume of this solid of revolution will go from a to b, which are these bounds on the x-axis, of pi f of x squared dx. So we will talk a little bit about where we got this formula from. The idea is if I do have some kind of function that I'm revolving around the x-axis, if I look at a single cross-section, once I've revolved it, I have a circle. So this cross-section is actually a circle. My axes will still go straight through the center. But we do have this circle here. Whenever I want to find the area of a cross-section, well, we would find the area of the circle, which would be pi r squared. And r is just your function. It's the height of your function, which gives us the pi f of x squared that we saw before. The disk method is just a particular variation of the general slicing method. Now let's do an example. We'll consider the function y equal to negative x squared plus 1 in the x-axis, and we're going to revolve around the x-axis. So if I think about what this looks like, it looks something like this, and we're going to revolve this region around the x-axis. We need to integrate. We need to know when this hits the x-axis, so when y is equal to 0. And if we solve this, we would get that x is equal to plus or minus 1. So these are my bounds of integration. We would then have pi times my function squared dx. I can pull the pi out front since it's just a constant. Squaring would give me x to the 4th minus 2x squared plus 1 dx. This gives me 1/5 x to the 5th minus 2/3 x cubed plus x between negative 1 and 1. Evaluating would then give me 1/5 minus 2/3 plus 1. Then we would subtract out negative 1/5 plus 2/3 minus 1, which gives us a volume of 16 pi over 15. We have another one where we're going to look at x squared, y equal to 0, and x equal to 2, and revolve around the x-axis. So this time my bounds will be 0 and 2, and then I would have pi times my function squared. We can remove the pi, have the integral from 0 to 2 of x to the 4th dx, which would then be over 5. We'll rewrite that. 1/5 x to the 5th from 0 to 2. Evaluating, we have 1/5 times 2 to the 5th, which is 32 over 5 minus 0. So my answer, 32 pi over 5. Next, we'll look at x cubed minus x plus 1, x equal to negative 1, and 1. If we look at what this looks like, our graph will look something like this. Here's negative 1, and here's 1. Our function will come up and go back down, like this. So our integral will be between negative 1 and 1, and then we have pi times the function squared, dx. We can remove the pi to the front between negative 1 to 1, and if we multiply this out, we get x to the 6th minus x to the 4th plus 2x cubed plus x squared minus 2x and then plus 1 dx. Integrating this would give me 1 over 7 x to the 7th minus 1 over 5 x to the 5th plus 1/2 x to the 4th plus 1 over 3x cubed minus x squared plus x, all between negative 1 and 1. And if we try to evaluate this, we would get 268 pi over 105. Our last example is a little bit different. This time I'm revolving y equal to x cubed, x equal to 0, and y equal to 8, but I'm going around the y-axis rather than the x-axis. So instead of doing things in terms of x, I need to do them in terms of y. The first step before was to figure out where you intersected the x-axis. Now I'm looking at limits of integration on my y-axis, 0 to 8. And then we look at the function in terms of y. Since y is equal to x cubed, we know that x is equal to the cube root of y. So I need to integrate pi times y to the 1/3 squared, which is 2/3, dy. Adding 1 to the exponent would give us 5 over 3. So we have 3 over 5, y to the 5 over 3, going between 0 and 8, and we need to multiply that by pi. Evaluating at 8 would give us 3 over 5 times 8 to the 5/3, which is 32. And then we would evaluate at 0, which would just be 0. Therefore, this gives us 96 pi over 5.